Hey guys, welcome back to chapter 17. We are going to move forward in the kinetics chapter, taking a turn away from average reaction rates and getting into kind of the second portion, which is instantaneous. So just as a reminder, we had talked about average reaction rates. So we had rate equals change in concentration over a change in time. We could look at concentration of reactants. We could look at concentration of products. But what we're looking at here was over some time period, right? So the analogy that I used was I could talk about my trip from here to Raleigh, and I could say over that entire trip, on average, I was traveling 60 miles per hour. What we're going to transition into is something called instantaneous reaction rates. So this is like a moment in time. So maybe I was traveling an average of 60 miles an hour to Raleigh, but as I was on 40, there was a police officer and he clocked me at 75 miles per hour, right? That's instantaneous reaction rate. So making the shift into instantaneous reaction rate, this is going to be the rate at which a reaction is proceeding at a specific time and at a specific concentration. So we're going to be looking at graphs for concentration versus time. We're going to be looking at graphs of concentration versus rate. So we'll be looking at those two in combination with one another. We're going to have kind of two layers to this instantaneous rates. We're going to have rate laws. That's going to be like the first half of this chapter. That's where we'll end. And then the next module, if you're in my online class, and the second half of the chapter will be integrated rate laws. So that's kind of the next step in the process. Okay. So let's explore this rate law. So the rate law is going to show how the rate of a reaction depends on the concentration of reactants. So if I were to summarize that statement, I would say we're looking at concentration of reactants versus rate. Those are the two pieces that we're going to be looking at. Anything in this chapter must be determined experimentally. You cannot look at an equation and know anything about it without the data. So the data is going to drive the statements that we make about rate. So changing the initial concentration of a reactant will affect the rate of the reaction. So here's a really cool demo that I'm going to pull up that shows the types of things that we're going to be looking at and talking about. All right, in this reaction, there's oxygen trapped in the Erlenmeyer flask. In his little spoon, he is lighting sulfur on fire. So what we see is it's burning, right? So obviously it's burning. There's oxygen in the air. Now we're going to introduce it to a much more oxygen-rich environment. And so we increase the concentration of oxygen. Clearly the rate of that reaction speeds up, right? So a little bit of oxygen slow, a lot of bit of oxygen very fast. Now we're going to take it out of that oxygen-rich environment. So now we're reducing the concentration of oxygen, and it slows down. We increase the concentration of oxygen, it speeds up. Okay. So what this video is showing us is the rate of the reaction is very much dependent on the concentration of reactants. Increased concentration, the rate is a lot faster, right? We see a lot quicker of a fire, and we reduce the amount of reactant, oxygen. There's still a fire, it's still proceeding, it's just not as fast. So that's just a really cool, easy demo to explain how concentration and reaction rates are related. So we're going to write something called a rate law to quantify this process. Rate law, it's going to be rate equals. So here's one of those times where I'm going to have to be very clear. If I'm asking about average reaction rates, we'll use the equation that we discovered in the first two videos. If I'm talking about anything else, or if I'm talking about if there's like a concentration in there somewhere, it's probably going to be rate law. Okay, so I'll be very explicit about average reaction rates. I'll be less explicit about the rate law. So assume rate law unless you see that word average. So we're going to use this following formula, just your very basic A, one-sided arrow, product. What you'll find in this part of the chapter is we actually don't talk much about products, so that's why I just wrote the word product, because we actually don't talk much about it. We're going to be more focused on the reactants. So for this chemical reaction, we can write the following rate law. So here's our equation, rate equals, so this is how we're going to quantify the rate. So rate equals rate constant K times the concentration of our reactants raised to the power, which we'll talk more about that. Okay, so let's break this down. Concentration of A, so that's the same concentration we've been looking at for the last 3 chapters, so that's in molarity, right? This rate constant K is a constant for a particular reaction at a given temperature. So if this reaction is for A, this rate constant is for this particular reaction. We change the reaction, we change the constant. We change the temperature, this constant also changes, but we'll dive into that in the second half of this module. This last thing we have here is this rate law exponent. We'll refer to it as the reaction order. Okay, the reaction order will be determined experimentally. So in the next video, we're going to look at how we determine the value for that. Is it a 0? Is it a 1? Is it a 2? So we'll talk about how we determine that. But what that tells us, what the rate law exponent or the reaction order tells us, is how the rate depends on concentration. Is there really strong dependence on it, which we saw in the demo video where it significantly increased? Is there just a little bit of dependence on it where, yeah, we see a big change in concentration, but it only speeds up a little bit? Or is there absolutely no relationship where I increase the amount of reactants and nothing changes? So that's what that reaction order is going to tell us, is how rate depends on concentration. Here's the different reaction orders that we are going to explore. So we're going to have an instance where N equals 0. We'll call that a 0 order. N equals 1, that's first order. N equals 2, that's second order. When we're talking about an individual reactant, it will not go over second order for us. Does third order exist? Technically, yes, but it's really, really rare, okay? So when we're talking about individual reactants, that would be a rare case. All right, so let's just take a look at this example. So the rate law for this particular reaction, so I have determined experimentally that this is a first order reaction, this N2O5. So I would write the rate law as such. Rate equals K times the concentration of my reactant And then again, that 1 in this case is implied. If it was a 0, there would be a 0 there. If it was a 2, there would be a 2 there. Okay. The problem, another problem, but kind of the limitation here is not many reactions are just a single reactant. Okay, I was able to find one. I was able to find an example where reactant breaks down. Quite often our reactions are a bit more complex, right? So quite often there's 2 or 3 reactants at play. So let's just see what the rate law would look like if there's more than one reactant. So we're going to go back to a generic equation where A plus B equals the product. This should not be here. So A plus B equals the product. Okay. If I were to write the rate law for this particular reaction, I would write rate equals, so always be rate equals. We'll always have a rate constant K. Then I would do concentration of my first reactant and raise it to some order times the concentration of my second reactant raised to its own order. Okay, so that's kind of the general outline for the rate law equation where, oh, I used the wrong letters. Change this a little bit. M, N. All right, so this is the general rate law equation where M is the order with respect to A, so it could be 0, 1, 2. N is the order with respect to B, it could be 0, 1, 2. And each of those would be determined experimentally. Okay. We will also talk about the overall order of the reaction. So the overall order of the reaction would just be simply adding together the orders for each individual reactant. So in this case, M plus N. So that's kind of your general overview of the rate law, getting to know it, getting some terminology knocked out. In the next video, we're going to talk much more about what a 0, first, and second order means. And then the video after that, we'll talk about how do we experimentally determine if it's 0 or first or second. So that's kind of a preview of what's to come. I hope you guys found this helpful.